There is a place where physics itself stops working. Our journey begins at the Big Bang Singularity, a point where the cosmic rules we rely on dissolve into pure mystery. As Stephen Hawking once noted, the universe does not allow perfection, and this is where that imperfection becomes absolute. This video will give you a complete picture of how our fundamental understanding of reality fractures at the edge of creation. We will see how Einstein's relativity fails, how quantum mechanics offers no answers, and why this is the central obstacle to a final theory of everything. We will confront questions without answers, like what could possibly exist before time itself. By the end, you will grasp why this singular moment is not just a scientific problem, but a profound limit to human knowledge. What does it mean for our reality to have a true beginning? The heart of this cosmic mystery is not a place you could ever visit. It is a mathematical boundary, a point of infinite density compressed into zero volume. All the energy that would become every star, every planet, and every one of us was contained there, but this was no ordinary container. The Big Bang Singularity is not an explosion that happened somewhere in space. It is the moment space and time themselves began to exist. Before that, the very concepts of before and after have no meaning. This idea emerges directly from Einstein's theory of general relativity, which describes gravity as the curvature of spacetime by mass and energy. The equations tell us that if you rewind the expansion of the universe far enough, all matter and energy converge to a single point of infinite curvature. The physicist Roger Penrose helped prove that such singularities are not flaws in the math, but inevitable predictions. They represent a hard edge to reality, a boundary beyond which the equations of general relativity simply spit out nonsense. To say the singularity has infinite density is not to describe an unimaginably large number. It is a sign that our mathematics has broken down completely. Density is mass divided by volume, but if the volume is truly zero, you are attempting to divide by zero. It is like asking your calculator to perform that operation. The result is not a gigantic number, it is an error. This mathematical error translates to a physical crisis. At the singularity, the geometry of spacetime itself becomes infinitely curved, tearing apart the very fabric that defines distance and duration. Causality, the rule that cause must precede effect, ceases to function. Predictability evaporates. There is no before to cause and after. So what does it mean to say the universe emerged from nothing? This nothing is not an empty void. Empty space is something, a stage with properties. This is a deeper, more absolute nothing, where not even the stage exists. Understanding this profound strangeness is the first step. It shows us why our most powerful theory of the large, Einstein's relativity, meets its ultimate limit here, setting the stage for a confrontation with the rules of the very small. Yet the very equations that gave us this prediction are the same ones that shatter at the moment of creation. General relativity is a masterpiece of human thought, a theory so precise it can predict the orbit of Mercury and the lensing of distant galaxies. Its core idea is beautifully simple. Massive objects like stars and planets tell the fabric of spacetime how to curve, and that curved geometry then tells everything else how to move. It is a cosmic conversation between matter and the stage it performs upon. But take this elegant idea to its ultimate extreme. Compress all the matter in the universe into a single, dimensionless point, and the conversation turns into a scream. The mathematics describing the curvature of spacetime, something physicists call the Riemann curvature tensor, does not yield a large number. It becomes infinite. This is not a calculation, it is a mathematical breakdown. As the physicist Kip Thorne has explained at the singularity, the predictive power of general relativity completely fails. It is as if you had a flawless map of a continent, but when you try to zoom in on one specific, impossible point, the map just shows a blazing white error message. The geometry of spacetime isn't just warped, it is torn apart. The very concepts of here and there, of now and then, lose all definition. This failure manifests in several profound ways. First, the theory offers no possible definition of a before. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question uses language from within our universe to probe a state where that language has no anchor. Second, the idea of a past simply vanishes. In our normal reality, every event has a history, a chain of causes we can trace back. At the singularity, that chain is severed. There is no past to trace. This also challenges what scientists call cosmic censorship, the hopeful idea that nature hides its singularities behind event horizons, like the one shrouding a black hole. The Big Bang singularity is naked. It is not hidden, it is the beginning of everything we see. To make this concrete, consider the paths objects take through the universe. In relativity, these are called geodesics, the straightest possible lines in a curved space. Planets follow geodesics around the sun. Light follows geodesics as it travels. But at the initial singularity, these paths do not just end, they are never defined in the first place. There is no starting line for the cosmic race. So if our best theory of the large, of gravity and spacetime, produces only infinities and errors at the beginning, what does that tell us? It suggests that gravity, as described by Einstein, might not be a fundamental force. Perhaps it is an emergent property, a collective behavior that arises from something deeper, just as the smooth flow of a liquid emerges from the chaotic dance of countless molecules. With general relativity broken at the threshold of existence, we have no choice but to look to the other pillar of modern physics, the rules governing the realm of the impossibly small. But if gravity's elegant geometry shatters into infinities, perhaps the answer lies in the opposite domain, the chaotic and probabilistic world of the quantum. Here, particles behave like ghostly waves, existing in multiple states at once until observed. This framework has given us the Standard Model, a stunningly accurate catalogue of the fundamental forces and particles. Yet, when we bring this quantum rulebook to the edge of the Big Bang, it fails just as spectacularly as relativity did. The problem is a fundamental mismatch of scales. Quantum mechanics exquisitely describes the behavior of the very small, like electrons and quarks. General relativity masterfully handles the very large and massive, like stars and galaxies. The primordial singularity, however, was both unimaginably small and contained all the mass in the universe. It demands a theory that can do both at once, a theory of quantum gravity. Without it, we are trying to describe a symphony using only the rules of individual notes, or an entire ocean using only the physics of a single water molecule. The conflict becomes starkly clear in a process physicists call renormalization. In the quantum world, calculations often spit out annoying infinities. For forces like electromagnetism, mathematicians developed clever tricks to subtract these infinities in a consistent way, yielding the finite, precise predictions we rely on. But when you try to apply these same tricks to gravity, the math refuses to cooperate. Gravity, in the quantum picture, becomes non-renormalizable. The infinities multiply uncontrollably, and no amount of mathematical cleverness can sweep them away. This means the probability for any quantum gravity event, calculated with our current tools, doesn't come out as 90% or 1%. It comes out as infinity%, a clear signal that our equations are meaningless. To understand why, consider a simple quantum principle, the uncertainty principle. It states you cannot know both the exact position and exact momentum of a particle. The more you pin down its location, the more wildly uncertain its energy becomes. Now, apply this to spacetime itself at the moment of creation. To measure the exact geometry of the universe at the singularity, you would need to confine it to an infinitesimal point. The uncertainty principle retaliates by making the energy fluctuations at that point infinite. You would need infinite energy to make the measurement, which is impossible. This suggests that spacetime itself may be subject to quantum uncertainty. Perhaps it is not a smooth, continuous fabric, but something granular, woven from discrete, tiny loops or pixels, as theorized by physicists like Carlo Rovelli in loop quantum gravity. In this view, there is a smallest possible unit of space, a quantum of volume, preventing the infinite collapse to a true singularity. This introduces another profound puzzle, the problem of time. In general relativity, time is part of the dynamical spacetime geometry. In standard quantum mechanics, time is an external background, a stage on which the quantum events play out. But at the beginning, there is no external stage. So what does the quantum wave function of the entire universe even wave in? How do you apply quantum rules when there is no clock outside the system to measure against? We are left with a powerful and humbling realization. Both of our crown jewel theories, each proven correct countless times in their own domains, become silent at the moment we most want them to speak. Their combined failure is not a minor gap but a chasm in our understanding. It forces us to ask a startling question. Is our intuition about reality, that it is smooth and continuous, fundamentally wrong? Could the universe be built from discrete, digital bits at the tiniest scale? This quantum dead end tells us we cannot simply glue our old theories together. We need to step back and consider frameworks that rewrite the rules from the ground up. This leaves us staring at a profound philosophical question disguised as a physics problem. If the laws break down, what set the cosmic clock ticking in the first place? The singularity presents the ultimate first cause dilemma. With no functioning physics, there is no mechanism to explain the initial conditions of our universe. Why did it have the precise density, the exact expansion rate, and the staggering uniformity we observe? These are not small details. They are the foundational settings, and they appear astonishingly fine-tuned. The physicist Alan Guth, who developed the theory of cosmic inflation, once noted that the universe is the ultimate free lunch, but it came with a very specific set of instructions. Without a theory of what happened at the very beginning, those instructions seem arbitrary, a random selection from an infinite number of possible starting points. To understand the depth of this mystery, we must look to the first fleeting moment, a period called the Planck Epoch. This was the first tiny fraction of a second after the singularity, a duration so short it is almost meaningless in human terms. During this epoch, the universe was smaller than a single atom, and the energy densities were so extreme that quantum gravity reigned supreme. This is the era we know nothing about. Our ignorance of those first moments is not a minor gap. It is a fundamental blind spot that propagates forward through all of cosmic history. The conditions set during the Planck epoch determined everything that followed, from the formation of the first elements to the birth of galaxies. It is as if we are trying to understand the plot of an epic film, but the first scene is pure static. We see the characters and the drama, but we have no idea what motivated them to begin. Think of it like a computer program. The universe runs on the elegant code of physical law, but at the singularity, it is as if the program crashes before the first line executes. We can study the output, the beautiful and complex cosmos we inhabit, but we cannot read the source code that initialized it all. This leads to the unsettling idea of fine-tuning. The expansion rate, for instance, had to be balanced on a razor's edge. A little faster, and matter would have flown apart too quickly to ever coalesce into stars and planets. A little slower, and gravity would have pulled everything back into a catastrophic collapse long ago. The initial uniformity, seen in the cosmic microwave background, is another puzzle. How did regions of the early universe that were causally disconnected, meaning light had no time to travel between them, end up at exactly the same temperature? This fine-tuning seems improbably precise, as if the dials were set just right for complexity and life to eventually emerge. So we are forced to ask, is the concept of a beginning even valid, or is it a limitation of our language and intuition? We instinctively search for a first cause, a starter button, but at the edge of reality, where time itself loses its meaning, that search may be fundamentally misguided. Perhaps what we call the beginning is not a point in time, but a boundary to time. This mystery of origin pushes us to reconsider the most familiar dimension of all, the very flow of time, which behaves in the strangest possible ways when stretched to its limit. The concept of a first cause relies on a chain of events, but what if the chain has no first link? At the singularity, the domino effect of reality encounters its ultimate paradox. The very first domino is not just missing, it is a logical impossibility. This is where causality, the unbreakable rule that cause must precede effect, dissolves into pure geometry. In the framework of general relativity, the Big Bang singularity is not a point in time. It is a boundary to time. Physicists describe it as a place where all time-like curves, the possible paths through spacetime that any particle or person could take, simply end. You cannot travel further back because there is no further back to travel to. There is no prior location on the map. Stephen Hawking, in his no-boundary proposal, offered a profound way to visualize this. He suggested that near the origin, the distinction between time and space blurs. Imaginary time, a mathematical tool, becomes dominant, and the usual flow of time becomes more like just another direction in space. Think of it like the Earth's surface. If you stand at the North Pole, the concept of going north loses all meaning. Every direction you face is south. The North Pole is not a place you can travel north from, it is the boundary of that concept. Similarly, the Big Bang is the boundary of before. Asking what happened before it is like asking what is north of the North Pole. The question uses language that only makes sense within the universe to probe a state where that language has no anchor. This leads us to the block universe view, where all of spacetime exists as a single, four-dimensional structure. In this view, the past, present, and future are all equally real, laid out like frames in a film. The Big Bang is not the first frame exploding into being. It is the edge of the film strip itself. There is no frame zero. This has staggering implications. It means there is no first moment in time, just as there is no southernmost point on a globe. There is only the beginning of the coordinate system we use to measure. This challenges our deepest intuitions about thermodynamics and entropy, the so-called arrow of time that points from order to disorder. If time has no true starting point, where does this arrow come from? Perhaps time as we experience it, with its relentless forward march, is not fundamental. It might be an emergent property, a large-scale illusion that arises from the increase in disorder, much like the concept of wetness emerges from the collective behavior of water molecules, even though no single molecule is wet. So we must confront a dizzying possibility. The flow of time, the very sensation of now slipping into then, may be a story our brains tell us about a universe where all moments coexist. If time itself is an emergent structure that crystallized from a more fundamental state, then the singularity marks the point where that structure was not yet built. With the dissolution of time, the stage of reality loses its most fundamental dimension, forcing us to examine the bizarre and equally unstable nature of the space that remained. If time loses its meaning at the edge, then space undergoes its own catastrophic vanishing act. Picture a map of the world, but as you zoom in on a single city, then a street, then a single atom on that street, the map doesn't show more detail. Instead, the lines themselves begin to blur and merge until the entire concept of distance dissolves into a formless gray. This is not a flaw in the map. It is what happens to the geometry of the universe itself at the singularity. The very stage upon which reality plays out ceases to have any definable shape or size. All of the vast, three-dimensional expanse we take for granted collapses into a state where here and there are the same word. This breakdown is captured in the heart of Einstein's equations by something called the metric tensor. Think of this as the cosmic rulebook for measuring things. It tells you the distance between 2 points, the angle between 2 lines, the entire geometry of spacetime. In our everyday world, this tensor gives us sensible, finite numbers, but rewind to the initial moment, and every entry in this cosmic rulebook explodes to infinity. The equations scream that the distance between any 2 points, no matter how you define them, becomes both zero and infinite simultaneously, a logical impossibility that signals the complete failure of our description. Physicists like James Hartle have approached this problem by asking a radical question. What if we stop thinking of the beginning as a point in a pre-existing space and instead describe it with a quantum wave function for the entire universe? In this view, there is no classical geometry at the start. There is only a probability cloud for potential geometries, a fuzzy superposition of every possible shape the universe could have taken. The familiar, smooth, expansive space we inhabit then crystallizes out of this quantum haze, much like a clear ice crystal forming from turbulent water. This leads to the mind-bending idea that location itself is not fundamental. At the singularity, you cannot say the universe is here or there, because those words require a background space to have meaning. It is an undifferentiated state, a cosmic blankness where geometry has not yet been born. Some theories, like the BKL conjecture, propose that as you approach this state, the collapse isn't smooth. Instead, space might have undergone chaotic, oscillatory convulsions, with different directions expanding and contracting in a violent, unpredictable dance. On an even smaller scale, quantum gravity suggests the fabric of spacetime might resolve into a seething quantum foam, a turbulent sea of virtual black holes and wormholes blinking in and out of existence, where the very notions of before and after, or near and far, are meaningless. To make this concrete, imagine a scientist with a perfect ruler trying to measure the diameter of the universe at the exact instant of the Big Bang. The calculation would be the total volume divided by the surface area. But if the volume is zero, you are dividing by zero. Your calculator flashes an error. This is not a limitation of the tool, it is a statement about reality. The question itself has no answer. So we must ask, is space, like time, an emergent property? Could the 3 dimensions we move through be the result of a deeper, more fundamental network of relationships, perhaps between quantum bits of information? This spatial collapse is inextricably linked to another parameter that reaches an impossible extreme, one that defines the very energy of creation. The collapse of space and time drags every other physical concept down with it into an abyss of impossibility. Among the first to shatter are the very laws of heat and energy. The temperature at the singularity wasn't just astronomically high, it was mathematically infinite. Think of the core of the hottest star, a raging nuclear furnace. Now imagine compressing the entire universe's worth of energy into a single point. The forge of creation wasn't just burning, it was a thermodynamic catastrophe where the rulebook was set on fire. Our understanding of heat and work, governed by thermodynamics and statistical mechanics, relies on one fundamental premise, that systems are composed of a finite number of particles behaving in statistically predictable ways. At the singularity, with infinite density, that premise evaporates. The physicist David Tong once framed the absurdity this way: if your theory predicts an infinite temperature, it is not describing a very hot state, it is telling you that you have asked a question your theory cannot answer. It is the ultimate error message. To give this chaos a scale, physicists define an upper limit called the Planck temperature, a number so vast it is essentially 1.4 times 10 to the 32 degrees Kelvin. Beyond this temperature, the energy of individual particles becomes so great that their quantum gravitational effects dominate, and our current theories lose all grip. The singularity, by definition, exceeds even this unimaginable limit. What does it mean for thermodynamics to break down? Consider the cornerstone concept of thermal equilibrium, the state where energy is evenly distributed and temperature has a single, clear value. In the primordial inferno, equilibrium was impossible. With energy density soaring to infinity, there was no stable state for the system to settle into. The frantic dance of particles would have been so violent that any attempt to define an average temperature would be like trying to calculate the average speed of cars in a traffic jam, if the number of cars and their possible speeds were both infinite. The result is not a number, it is nonsense. This leads directly to the collapse of entropy, the measure of disorder that gives time its arrow. In our universe, entropy always increases, driving processes from order to chaos. But at the beginning, in a state of infinite temperature and density, the very concept of entropy becomes meaningless. You cannot have more or less disorder when the system is already in a state of ultimate, infinite chaos. There is no gradient, no direction for change, so we are left with a haunting question: is this infinite energy a physical reality? Or is it the most glaring sign yet that our physics is incomplete? The infinite is not a number we can reach, it is a boundary we cannot cross. It is a mathematical placeholder for our profound ignorance, a glaring spotlight on the point where our understanding of energy and matter dissolves into pure mystery. This energetic chaos did not exist in isolation. It directly governed the behavior of the universe's most fundamental ingredients. This chaotic energy did not just break the laws of heat, it dissolved the very architecture of reality. Our universe is governed by four fundamental forces, each with its own distinct personality. Gravity sculpts galaxies, electromagnetism binds atoms and gives us light, the strong nuclear force glues atomic nuclei together, and the weak force drives radioactive decay. For decades, a central goal of physics has been to unify these forces, to show they are all different facets of a single, elegant superforce. This dream of unification seems to reach its ultimate fulfillment at the singularity, where energy levels become infinite. In that unimaginable forge, the distinctions between gravity and electromagnetism, between the strong and weak forces, should vanish completely. They should merge into one unified law. Yet here lies a profound paradox. At the very moment of perfect unification, the framework for that unification itself collapses. It is a cosmic bait and switch. The theories that aim for this grand synthesis, known as grand unified theories, and the more ambitious theories of everything, all share a critical assumption. They require a stable vacuum state and well-defined quantum fields to operate. Think of these fields like the calm surface of a pond. You can drop a pebble in and watch the ripples, the particles, propagate in predictable ways. But at the singularity, there is no calm pond. The vacuum itself is in a state of infinite fluctuation, a roiling, seething chaos where the very idea of a stable background ceases to exist. As string theorist Brian Greene has noted, even string theory, our most sophisticated candidate for a theory of everything, struggles at this regime. Its equations, which rely on vibrating strings in a 10 or 11-dimensional space, presuppose a stage upon which those strings can dance. At the singularity, the stage is being born and annihilated simultaneously. It is like trying to perform a symphony while the concert hall is still exploding into existence. To understand the scale of this failure, we must distinguish between two epochs. There is the Grand Unification Epoch, a period almost immediately after the Planck time, where the three quantum forces, electromagnetism, and the strong and weak nuclear forces, are believed to have merged into one. This is a realm of extreme but finite energy that our theories can at least attempt to describe. Then there is the Planck epoch itself, the domain of the true singularity, where gravity joins the fray and energy becomes infinite. This is the true unknown. Here, the forces don't just unify, they become indistinguishable and then meaningless. Imagine a painter's palette holding every possible color. As the painter mixes them, seeking the pure essence of color, they eventually blend into a single shade, a blinding, featureless white. This white contains all colors, yet it conveys no information, no structure, no beauty. It is unity without meaning. The singularity is that blinding white. All forces are present, but they have lost their defining characteristics. There is no difference to measure, no interaction to calculate. The quest for a single, beautiful equation that describes the cosmos hits a wall not of complexity, but of emptiness. So we are forced to ask a startling question. Is our entire approach, the search for a unified law of physics, fundamentally flawed when applied to the absolute beginning? Perhaps the laws of physics are not eternal, timeless truths. Perhaps they, like time and space, crystallized out of the chaos. They may be emergent properties, cosmic habits that settled into place as the universe cooled and expanded, rather than pre-existing commandments. This realization forces us to look beyond our familiar equations and consider a far more radical description of that first moment. The reliable grammar of the universe is mathematics, but at the singularity, this grammar begins to stutter and fail. For centuries, we have trusted equations to describe reality, from the arc of a thrown ball to the orbit of a distant planet. Yet when we apply our most sophisticated mathematical languages to that first moment, they produce not answers but paradoxes, like a sentence that contradicts its own meaning. The great mathematician and physicist Henri Poincaré warned that while mathematics gives us the method, it is physics that must provide the reality. At the edge of the Big Bang, the method breaks down, leaving reality shrouded in mystery. Consider the primary tools we use to map the cosmos. Differential geometry describes the smooth curvature of spacetime, while tensor calculus handles the complex relationships within that curvature. Quantum field theory calculates the probabilities of particles popping in and out of the quantum vacuum. Each is a masterpiece of logic, but feed the conditions of the singularity into these frameworks, and they yield pathological solutions. In mathematics, a pathological solution is one that is mathematically valid but physically nonsensical, like a formula predicting a planet with negative mass or a journey that takes less than zero time. The singularity is the ultimate pathological result. It is what you get when you push a beautiful equation far beyond the domain where its assumptions hold. A key distinction lies in the type of singularity we face. Some are merely coordinate singularities, artifacts of an awkward choice of measurement system. Think of the lines of longitude on a globe. They all converge at the North Pole, making the longitude coordinate undefined there. But the pole itself is a perfectly normal point on the sphere. You can choose different coordinates to remove the apparent problem. The singularity at the heart of a black hole's event horizon is often like this, but the Big Bang singularity is different. It is an essential curvature singularity. No matter how cleverly you change your mathematical coordinates, the curvature, the actual warping of spacetime still blows up to infinity. You cannot smooth it away. The problem is not in our map, it is in the territory itself. To see a simpler version of this, look at the function 1 divided by x. As x gets closer and closer to 0 from the positive side, the value of 1 divided by x shoots off toward positive infinity. From the negative side, it plunges toward negative infinity. At the exact point x equals 0, the function is simply undefined. Infinity is not a number you can plug into the next step of a calculation. It is a sign that you have left the system. The mathematics of the real number system has no vocabulary for this. This is precisely what happens with the density and curvature in our cosmological equations. The output is not an unimaginably large number, it is an error code. This failure manifests profoundly in our attempts to apply quantum theory. The standard technique called perturbation theory works by treating complex interactions as small tweaks to a simple, solvable system. It is like understanding the orbit of Earth around the Sun first by ignoring the Moon, then adding the Moon's gentle pull as a minor correction. But at the Planck scale, gravity's influence is not a gentle tweak, it is the entire game. The corrections are not small, they are infinite. The perturbation series diverges, meaning the more terms you add to try to improve accuracy, the worse and more nonsensical the answer becomes. The approach itself is invalid, so we are left at a profound impasse. If our trusted mathematical languages produce only infinities and errors, does this mean we need an entirely new mathematics to describe the beginning? Some physicists look to realms like category theory, which focuses on the relationships between objects rather than the objects themselves, or non-commutative geometry, where the order in which you perform operations matters fundamentally, much like the difference between putting on your socks and then your shoes versus the other way around. These are not just more complex versions of old math, they are different ways of thinking about logic and structure altogether. This mathematical dead end is precisely why cosmologists have been driven to propose such creative models for the universe's origin. Ideas like the cyclic universe, the quantum bounce, or the multiverse are not wild speculations made in a vacuum. They are desperate, ingenious attempts to construct a narrative that avoids the singular, nonsensical point where all our equations die. They are stories written in a new grammatical tense, one where the sentence of the cosmos does not begin with a paradoxical word. Faced with a mathematical dead end, we must ask if the problem lies in the story we are telling. What if the universe never passed through a singular point of infinite density at all? A growing chorus of cosmological models suggests exactly that, proposing elegant narratives where the Big Bang is not a beginning but a transformation. These frameworks offer potential escape routes from the singularity, not by ignoring the laws of physics, but by applying them more completely. They replace the violent, nonsensical break with a smooth quantum transition, suggesting our cosmos is part of a far grander cycle. Physicist Neil Turok, a proponent of cyclic models, describes the universe not as a one-time explosion from nothing, but as a kind of cosmic heartbeat, an eternal rhythm of expansion and contraction. In this view, each Big Bang is preceded by a big crunch, where the universe contracts to an extraordinarily dense state, but not to a true singularity. At the moment of maximum compression, quantum gravitational effects become dominant. Instead of allowing an infinite collapse, these effects turn gravity from an attractive force into a repulsive one. Picture a spring, compress it with all your might. Just when you think it cannot shrink further, it pushes back with tremendous force, launching itself outward. This is the essence of a quantum bounce. The universe reaches a minimum possible size, a smallest meaningful volume dictated by quantum geometry, and then rebounds into a new phase of expansion. This is not science fiction, but a prediction emerging from specific approaches to quantum gravity, like loop quantum cosmology. In this framework, spacetime is not infinitely divisible. It is woven from tiny, discrete loops, giving it a fabric with a finite, smallest possible weave. When the universe contracts to near this scale, the equations show that the curvature does not blow up to infinity. Instead, it reaches a maximum value and then smoothly transitions, causing a repulsive force that drives the bounce. The singularity is replaced by a cosmic bridge. Another profound alternative is the Hartle-Hawking no-boundary proposal. Remember the problem of what happened before the Big Bang. Hartle and Hawking suggested we stop thinking of the beginning as a point in time at all. They proposed that if we trace the universe back to its origin, the dimension of time smoothly morphs into a dimension of space. Think of the Earth again. The South Pole is a point, but if you approach it, lines of longitude converge. In the Hartle-Hawking state, the beginning of the universe is like the South Pole of a globe. It is a perfectly smooth, rounded point, not a jagged, tearing hole in reality. There is no boundary, no edge where the laws break down. In this model, asking what happened before the Big Bang is as meaningless as asking what is south of the South Pole. The question simply dissolves. Each of these models makes distinct predictions. A cyclic universe might leave faint imprints in the cosmic microwave background, subtle patterns from a previous cosmic era. A bouncing model predicts a specific signature in the distribution of the very first structures in the universe. The no-boundary proposal gives a specific probability for the universe to have the smooth, uniform geometry we observe. Yet all face significant challenges. The cyclic model must solve the problem of entropy, explaining how each new cycle resets the universal disorder. The quantum bounce requires a complete and tested theory of quantum gravity, which we still lack, and the no-boundary state, while mathematically elegant, is difficult to connect to the specific, lumpy universe we see around us. So do these ideas truly solve the mystery of origins, or do they simply relocate it? A cyclic universe still demands an eternal, unexplained rhythm. A quantum bounce requires a pre-existing state to bounce from. The no-boundary proposal elegantly removes the boundary, but it does not explain why this particular smooth geometry emerged over any other possibility. Perhaps the ultimate lesson is this: removing the mathematical singularity is a crucial step, but it does not erase the profound philosophical question of why there is something rather than nothing. It trades one type of mystery for another, shifting the focus from a catastrophic breakdown to the enigmatic laws that govern transitions between states of reality. This forces a humbling realization: to understand the origin of everything, we may need to let go of the idea of an origin altogether and embrace a cosmos whose true nature operates on a logic far stranger than our intuition can grasp. If the laws of physics break down, perhaps the stage itself is not what we think. At the very smallest scales, the smooth, continuous fabric of spacetime dissolves into a turbulent, probabilistic sea. This is the realm of quantum foam, a concept introduced by the physicist John Wheeler, who described spacetime as foam-like. Picture not a calm, woven fabric, but the surface of a pot of water at a rolling boil. Bubbles of all sizes form and burst in a frantic, chaotic dance. At any given instant, can you point to a single, stable water molecule and say this is the definitive surface? No, because the surface is a statistical average of the frenzied activity below. Quantum foam is like that, but for reality itself. At scales of around 10 to the negative 35th meters, the so-called Planck length, the Heisenberg uncertainty principle wreaks havoc on geometry. This principle tells us we cannot precisely know both energy and time. The shorter the time interval you examine, the more wildly uncertain the energy becomes. Apply this to the fabric of spacetime, and it means that over incredibly tiny distances and durations, the energy of the vacuum is not calm and empty. It is a seething cauldron of violent fluctuations. These aren't fluctuations of particles in space, they are fluctuations of space itself. The curvature, the very shape of spacetime, undergoes random, chaotic convulsions. In this foam, Wheeler suggested, virtual particles and even tiny wormholes blink in and out of existence, borrowing energy from the vacuum for fleeting moments before vanishing. This is the same vacuum energy, or dark energy, that we now see driving the accelerated expansion of our universe on the largest scales. Its roots may lie in this microscopic frenzy. So what does this mean for the singularity? The idea of a single, infinitely dense point relies on the assumption that spacetime is a smooth, classical backdrop right down to zero size. But if spacetime is inherently foamy and discontinuous at the Planck scale, then the concept of a mathematical point with perfect definition loses all meaning. You cannot compress the universe into something smaller than the smallest possible grain of reality. The terrifying singularity of infinite density gets smeared out, replaced by a probabilistic cloud of potential geometries. The universe's origin is not a pinprick but a quantum haze. Could the entire universe, then, be the ultimate quantum fluctuation? In this perspective, our vast cosmos might be a rare but statistically possible bubble that stabilized in the eternal quantum foam, a single fluctuation that grew and did not immediately pop. This intertwines the fate of the singularity with the deepest question of all, whether something can truly emerge from nothing, if that nothing is a seething, probabilistic sea of potential. But what if this quantum foam is not just the texture of reality, but its very source? The most radical answer to the origin of everything is that the universe, including the singularity we have been wrestling with, simply tunneled into being from a state of absolute nothing. This is not magic, but a potential consequence of the strange rules that govern the quantum realm. At the heart of this idea is a process called quantum tunneling. In the everyday world, if you roll a ball up a hill but lack the energy to reach the top, it will always roll back down. In the quantum world, that ball has a small but real probability of suddenly appearing on the other side of the hill without ever having climbed over. It doesn't go over the barrier, it tunnels through it. This isn't a theoretical curiosity, it's the mechanism that allows stars like our sun to shine, as protons tunnel through electrical barriers to fuse together. Now apply this staggering concept to the cosmos itself. Cosmologist Alexander Vilenkin proposed a model where the entire universe quantum tunnels from a state of nothing into a state of something. In this framework, nothing does not mean empty space. Empty space or a quantum vacuum is still a something, a seething sea of potential energy governed by the laws of physics. Vilenkin's nothing is more profound. It is the absence of space, time, matter, and even the laws of physics themselves. It is a state about which, by definition, nothing can be said. From this absolute nothing, a tiny bubble of spacetime could spontaneously nucleate via quantum tunneling. Think of it like a bubble forming in a pot of boiling water, but here, the water itself is the concept of nothingness, and the bubble is a nascent universe complete with its own laws and dimensions. This process is described by the wave function of the universe, a mathematical object that assigns a probability amplitude for a universe with certain properties, like a specific size and expansion rate, to appear. It doesn't describe a universe evolving in time because time is created within the bubble. It gives us odds for different starting configurations. This forces a crucial distinction. When physicists speak of the universe coming from nothing, they often mean from a quantum vacuum, a state rich with latent energy and governed by quantum law. This is a scientific, though deeply counterintuitive, proposition. But true philosophical nothingness, the complete absence of anything, including laws and potential, is a concept that may forever lie outside the realm of science. If our universe did tunnel into existence, it shatters our classical notion of causality. We instinctively seek a cause that precedes an effect in time. But if time itself begins with the universe, then the concept of a preceding cause becomes meaningless. The universe wouldn't have a cause in the traditional sense. It would be an uncaused, quantum probabilistic event. This leads to an even more expansive thought. If one universe can tunnel from nothing, what prevents many? The same quantum principles that allow for one spontaneous nucleation could, over an unfathomable non-time, give rise to a vast multiverse, an endless froth of cosmic bubbles, each with its own unique physical laws. Some might collapse instantly, others might expand into barren voids, and a rare few, like ours, might have the precise conditions for complexity and life. In this view, the singularity we call the Big Bang was not the absolute beginning of all reality, but merely the beginning of our local cosmic chapter, one page in an infinite book whose first page we may never be able to read. The ultimate evasion of the origin question may be to declare there is no single origin at all. If one universe presents an intractable singularity, perhaps the answer is to propose an infinite number of them. This is the Multiverse Hypothesis, a framework where our Big Bang is not a unique creation event, but merely one bubble nucleating in an eternal, frothing cosmic sea. In this view, the problem of the initial singularity is not solved so much as it is diluted across an endless landscape of possibilities, moving the ultimate beginning to a realm that may forever lie beyond our observational reach. The most developed pathway to this staggering idea comes from a twist on cosmic inflation, the theory that our universe underwent a period of hyper-fast expansion in its first moments. Physicist Andrei Linde developed a version called chaotic eternal inflation. Here, the inflatoned field, the energy driver of this expansion, is not uniform. It has quantum fluctuations. In most regions, the field loses energy, inflation ends, and a stable, hot universe like ours forms. But in some regions, a random fluctuation kicks the field back up to a high energy state, causing inflation to continue there forever. The inflating background becomes a self-reproducing, eternal engine, continuously giving birth to pocket universes that pinch off into their own separate realities. Our entire cosmos is just one such bubble in an infinite, ever-growing metacosmos. There is no global beginning to the entire multiverse, only local beginnings for individual bubble universes. The initial singularity of our universe is then just a local feature, a boundary within our bubble, not a boundary for all of reality. To picture this, think of a gigantic, never-ending popcorn maker. The hot oil is the eternally inflating background space. Individual kernels are quantum fluctuations. When a kernel pops, that is a bubble universe like ours coming into existence and rapidly expanding. But the pot is so vast, and new kernels are constantly being added, that popping events happen at different times and places forever. There is no first pop, only an eternal process. This inflationary multiverse is not the only version. String theory suggests another, the landscape multiverse. Here, the extra dimensions predicted by string theory can curl up in a colossal number of ways, perhaps 10 to the 500 different ways. Each unique configuration corresponds to a different set of physical laws and constants a different universe. Our universe, with its specific, life-permitting numbers, is just one address in this vast, static landscape of possibilities. Then there is the quantum many-worlds interpretation, where every quantum decision branches reality into multiple timelines. While often discussed differently, in its most expansive form it too suggests a proliferation of realities. So, does the multiverse truly solve the singularity problem? In one sense, it reframes it elegantly. It replaces the hard wall of a beginning with an endless fractal coastline. There is no need for a first cause for the whole ensemble if the ensemble is eternal and self-generating. The troubling infinities of our singularity become a finite, local phenomenon within a much larger, potentially infinite structure. Yet profound challenges remain. By its very nature, the multiverse is notoriously difficult to test. If other universes are causally disconnected from ours, forever beyond the reach of any signal, can the idea ever be more than a compelling philosophical speculation? Some physicists argue that certain versions may leave subtle fingerprints in our cosmic microwave background, like patterns from collisions with other bubbles in the distant past. Others suggest the precise values of our constants, which seem improbably fine-tuned for life. themselves become inevitable predictions if every possible value exists somewhere. The multiverse, then, becomes a kind of cosmic selection effect. We find ourselves in a universe that permits our existence simply because that is the only type of universe we could ever observe. This leads to a pivotal reflection. Is the multiverse a genuine scientific theory, or is it an elegant escape hatch from the singularity problem? It pushes the ultimate question of origins one step back from our universe to the meta-realm that spawns it. We must then ask, what are the laws that govern the inflating background or the string theory landscape? Where do those laws come from? The multiverse may not erase the mystery, but it transforms it, trading the paradox of a single, violent beginning for the enigma of an eternal, fecund reality whose ultimate rules remain just as hidden. This expansive, almost philosophical view stands in stark contrast to the other path, the relentless drive to find a specific, testable framework that describes our universe's first moment with mathematical precision. String theory offers perhaps the most mathematically elegant escape from the singularity, a framework where the universe is not born from a point, but emerges from a transformation. In this view, the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The physicist Brian Greene has described this by saying that if we could peer down to the Planck scale, we might see that every particle is a note on a tiny vibrating string. The music of these strings, their specific vibrational patterns, determines whether they are an electron, a quark, or a particle of light. This simple shift from points to strings has profound consequences for the Big Bang. The most violent collisions of point particles can create infinite densities, but when strings collide, they do not concentrate energy into a single, zero-dimensional point. They smear it out along their one-dimensional length. This simple geometric fact begins to soften the harsh singularity, replacing a mathematical breakdown with a physical process we might actually describe. A specific scenario within string theory, developed by Gabriele Veneziano and Maurizio Gasparini, paints a dramatic picture of a cosmos that existed before our Big Bang. They propose a pre-Big Bang era where the universe was vast, cold, and nearly empty, dominated by a field called the dilaton. This dilaton field is unique to string theory, and it controls the strength of all forces. As this field evolved, it drove the universe into a phase of superinflation, causing it to contract at an accelerating rate. Imagine an orchestra where the conductor slowly raises their arms, and every musician draws their bow tighter and tighter across their strings, building towards a crescendo. The universe wasn't collapsing under gravity in the classical sense, it was being wound up by the dilaton. This contraction didn't lead to an infinite crunch. Instead, as the curvature and density reached the string scale, the theory's new physics took over. The energy stored in the dilaton field and the winding of the strings themselves created a tremendous repulsive force. The universe reached a maximum curvature and then bounced like a rubber ball hitting a floor made of quantum foam. The dilaton field stabilized, and its immense energy was dumped into creating the hot, dense soup of particles that marked the start of our conventional Big Bang expansion. The singularity was not a beginning but a turning point. This scenario is woven from several exotic elements central to string theory. First are the extraspatial dimensions, curled up so small we never perceive them. Their geometry is crucial, determining the properties of particles and forces. Then there are branes, multidimensional surfaces where strings can end. Our entire universe could be a three-dimensional brane floating in a higher dimensional space. Finally, the dilaton field acts as a master volume knob for the strength of gravity and other interactions. In the pre-Big Bang phase, this knob was turned in a way that made gravity incredibly weak, allowing the universe to contract without immediately collapsing into a black hole. All these components work in concert to orchestrate the bounce. Think of the universe not as an instrument that shatters, but as a cello whose string is plucked with such force that it momentarily vibrates in a wild, chaotic mode before settling into a deep, resonant note. The transition from contraction to expansion is that moment of chaotic vibration, a stringy phase where the old rules fade and new ones emerge. Yet for all its conceptual beauty, string theory presents a formidable challenge. Its mathematical complexity is staggering, and after decades of work, it has yet to make a single testable prediction that can be verified in a laboratory or by a telescope. The pre-Big Bang scenario, while compelling, is one of many possible narratives within the string theory landscape. We are asked to believe in extra dimensions, brains, and fields we have never directly observed, all to solve a problem that occurred in a regime forever beyond our direct observational reach. Does the elegance of the solution justify the sheer scale of unproven assumptions? This tension lies at the very heart of modern theoretical physics. String theory represents a breathtaking leap of imagination, a candidate for a theory of everything that seamlessly merges quantum mechanics and gravity by its very construction. But until it can point us toward a specific, observable signature in our universe, a faint pattern in the cosmic microwave background, or a new particle in a collider, it remains a magnificent and untested symphony, composed in the language of mathematics, waiting for the universe to play its first confirming note. String theory is not the only path that leads away from the singularity. A different, equally radical approach suggests that spacetime itself has a woven, granular structure, like the threads of a tapestry. This is loop quantum gravity, a framework where the smooth continuum of Einstein's universe dissolves into a network of intersecting loops. These loops are the quanta of space, the smallest possible units of area and volume. You cannot have half a loop, just as you cannot have half an electron. This discrete geometry provides a powerful escape clause from the infinite collapse. When applied to the entire cosmos, this idea blossoms into loop quantum cosmology, a rigorous model where the Big Bang is not a beginning but a big bounce. Pioneered by physicists like Abhay Ashtekar, this framework takes the equations of general relativity and rewrites them with the granularity of space baked in from the start. The result is a modified set of cosmic evolution equations. In the old story, as you rewind time, the universe's volume shrinks to zero and its density soars to infinity. In the new story, quantum geometry intervenes. As the density approaches a critical, immense value, a powerful repulsive force emerges from the quantum nature of gravity itself. Think of it like a spring. Compress a spring with all your might. At first, it resists gently, but push it toward its absolute limit, and the resistance becomes fierce, ultimately rebounding with tremendous force. In loop quantum cosmology, the universe is that spring. It contracts from a previous cosmic phase, but instead of crushing down to an impossible point, it reaches a minimum possible volume, a smallest meaningful size set by the quantum weave of spacetime. Then it bounces. The Big Bang becomes the moment of maximum compression and the launch into our current expansion. The mathematical heart of this lies in how the theory quantizes geometry. Area and volume can only take on specific, discrete values, much like the energy levels of an atom. This quantization acts as a cosmic regulator, preventing the curvature of spacetime from ever reaching infinity. The equations that once spit out nonsensical infinities now yield finite, sensible numbers throughout the entire transition. This is not a philosophical idea, it is a specific mathematical prediction. So what would such a bounce look like, and could we ever find evidence for it? The theory suggests that the universe would have carried some memory of its pre-bounce phase through the transition. This might leave subtle, specific imprints on the oldest light we can see, the cosmic microwave background. Certain patterns in that radiation, like specific irregularities in the polarization or temperature maps, could, in principle, be the faded fingerprints of a universe that existed before ours. While these signatures are incredibly faint and not yet detected, they offer a tantalizing possibility, a way to test a theory of quantum gravity not in a lab but in the sky. This presents a profound shift in perspective. It replaces the terrifying, unknowable singularity with a potentially knowable transition, yet it invites a deep, almost philosophical question. If our universe is one bounce in an endless cycle, does that feel more satisfying than a single, singular origin? A cyclic universe offers a kind of eternal rhythm, avoiding the need for a definitive start. But it does not erase the question of initial conditions, it simply moves it. What set the cycle in motion in the first place, or has it been turning forever? And if information or structure can survive the bounce, does that mean our universe is, in some way, an inheritance from a prior cosmic era? Loop quantum cosmology brilliantly removes the mathematical breakdown, but it leaves us contemplating a cosmos without a clear beginning, an infinite regress of expansions and contractions that challenges our very desire for a starting line. Yet even the fabric of spacetime might be a kind of projection, a cosmic illusion cast from a deeper reality. This radical idea is known as the Holographic Principle, and it suggests that all the information describing everything within a volume of space, from swirling galaxies to the thoughts in your mind, can be perfectly encoded on its two-dimensional boundary, like the data on a security hologram. When applied to the edge of the Big Bang, this principle offers a breathtaking way to sidestep the singularity entirely, by suggesting the terrifying interior was never the real story. The concept emerged not from cosmology, but from a deep puzzle about black holes. Physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its hidden information, is proportional not to its volume, but to the area of its event horizon. This was a profound clue. In our everyday world, entropy scales with volume. A larger box can hold more disordered arrangements of its contents, but a black hole's information capacity is limited by its surface area. It was as if all the data about what fell in was painted on its spherical surface. Leonard Susskind and Gerard T. Hooft took this clue and formulated a bold principle that perhaps this wasn't just a quirk of black holes, but a fundamental property of all space. The universe itself might be a hologram. To grasp this, think of a three-dimensional movie you watch in a theater. The breathtaking depth, the objects that seem to fly toward you, all of that rich information is not stored in the three-dimensional space of the theater. It is encoded on the two-dimensional film reel spinning through the projector. The holographic principle suggests our three-dimensional reality, with all its forces and particles, is a projection from a two-dimensional surface at the edge of the cosmos. This is made mathematically concrete through a discovery in string theory called the AD-SCFT correspondence. It shows a perfect equivalence, a dictionary, between a theory of gravity in a certain type of warped space and a quantum field theory without gravity, living on its boundary. The physics in the volume is exactly mirrored by the physics on the surface. There is no data loss, no contradiction. They are two descriptions of the same thing. Now apply this to the beginning. Our universe is not exactly like the specific space in that correspondence, but extensions of the idea suggest a similar logic could apply. If the very early universe was an incredibly high entropy, hot, dense state, akin to the interior of a black hole, then its complete description might live on its boundary, a surface at the moment of the Big Bang. The singularity, the point of infinite curvature and density that breaks our equations, would simply be an artifact of looking at the wrong description. It would be like trying to understand a movie by studying the chemical composition of the light beams in the air instead of reading the film reel. The true, fundamental theory of the beginning might be a non-gravitational quantum theory on that boundary, a conformal field theory which has no singularity at all. This leads to the ultimate question about information at the origin. In quantum mechanics, information is never destroyed, a principle called unitarity. But a classical singularity seems to erase it completely, shredding the rulebook of cause and effect. The holographic principle rescues this. If the true description is on the boundary, then information is preserved there. The chaotic interior, with its apparent singularity, is just a calculated projection, and the information survives intact on the lower dimensional surface. So we are left to wonder, is reality fundamentally made of information rather than space and time? Is geometry itself a secondary phenomenon, something that emerges from a vast network of quantum bits entangled on a distant surface? This informational perspective reframes the mystery of entropy at the beginning. The high entropy of the primordial fireball might not represent disorder in a three-dimensional sense, but a maximal encoding of data on a two-dimensional screen. The emergence of our structured, lower entropy universe could then be seen as a particular unfolding of that information into the three-dimensional world we experience. It suggests the origin of everything might not be a place, but a process of translation, where a lower dimensional code is rendered into the rich, geometric reality we call home. The smooth, holographic boundary of creation presents us with a profound contradiction. If the early universe was a hot, dense plasma, a state physicists typically associate with maximum chaos, why does it appear to have been born with such exquisite order? This is the puzzle of entropy and the arrow of time. Entropy is a measure of disorder, and the second law of thermodynamics states that it always increases in a closed system. This relentless climb from order to chaos is what gives time its irreversible direction, its arrow. We remember yesterday but not tomorrow because entropy was lower yesterday. Yet this entire majestic flow rests on a single, unexplained foundation, the past hypothesis. This is the assumption that the universe began in a state of incredibly low entropy. As physicist Sean Carroll has framed it, the real mystery is not why entropy increases toward the future, but why it was so astonishingly low in the past. The initial conditions were set to a precise, delicate order that seems to defy the chaotic singularity we have been exploring. To understand the staggering improbability of this, consider a deck of playing cards. A perfectly ordered deck with all cards arranged by suit and number represents an extremely low entropy state. A thoroughly shuffled deck is high entropy, disordered. The second law says a shuffled deck will never spontaneously become perfectly ordered. Yet, our observable universe is that perfectly stacked deck, appearing from what should have been cosmic chaos. One might suggest it was just a random fluctuation. In an eternally existing universe at equilibrium, extremely rare fluctuations can create pockets of order. But this leads directly to the Boltzmann brain paradox, named for the physicist Ludwig Boltzmann. The logic suggests it is vastly more probable for a single, fully formed, conscious brain to fluctuate into existence complete with false memories of a universe than for an entire, ordered cosmos like ours to do so. If we were merely random fluctuations, we should almost certainly be solitary Boltzmann brains drifting in a void, not coherent beings in a vast, structured universe. So the low entropy beginning is not a minor detail, it is the central enigma of time itself. Roger Penrose offered a profound geometric explanation called the Weyl curvature hypothesis. He proposed that the initial singularity was exceptionally smooth, with a special constraint that kept gravitational entropy, the disorder in spacetime's geometry, at a minimum. In this view, the Big Bang's smoothness was the ultimate form of order, and the clumping of matter into galaxies and black holes over billions of years represents the increase of gravitational entropy. The smooth beginning had low Weyl curvature, a specific measure of tidal distortion, while a chaotic singularity would have had it maximized. This elegantly ties the thermodynamic arrow of time directly to the geometry of the cosmos at its origin. Yet this simply reframes the mystery. Why was the whale curvature so constrained? Is this low entropy beginning a fundamental, unexplained law of initial conditions, a brute fact of our cosmos? Or could it be a selection effect within a vast multiverse? In an ensemble of infinite universes, perhaps only those that began with low entropy could ever develop complex structures, stars, planets, and observers like us. We find ourselves in such a universe because it is the only kind we could possibly inhabit. This orderliness at the threshold of existence stands in stark, almost paradoxical contrast to the infinite chaos predicted by the classical singularity. It forces us to ask whether the very concepts of order and disorder are meaningful at that ultimate boundary, or if the arrow of time itself is an emergent property that crystallized only after the universe found its footing. Our sense of a lawful cosmos rests on a deep assumption that from a complete snapshot of the present, the future can, in principle, be calculated. This is determinism, the philosophical bedrock of classical physics from Newton to Einstein. Yet at the threshold of the Big Bang, this comforting predictability meets its final, absolute death. Determinism does not merely become difficult, it becomes a logical impossibility. The equations that govern the universe's evolution require a starting point, a set of initial conditions you can plug into the cosmic calculator. At the singularity, those initial conditions are not just unknown, they are mathematically undefined. You cannot specify the position, velocity, or density of anything because the concepts of here and velocity and density lose all coherent meaning. It is like being asked to write down the starting coordinates for a journey, but the map you are given is a blank page smeared with ink. There is no data to input. This failure is not a minor glitch in the system. The Einstein field equations, which beautifully predict the orbits of planets and the bending of light, lose all predictive power when they cannot be seeded with initial data on a consistent slice of spacetime, what physicists call a space-like hypersurface. At the singularity, there is no such smooth slice on which to set your numbers. The geometry is so pathological that every possible starting surface crunches into the same nonsensical point. Therefore, even if a mythical Laplacian demon, an intellect with perfect knowledge of all forces and positions, existed at that moment, it would have nothing to know. Its vast calculation would crash before the first step. This is where chaos, in its most profound mathematical sense, takes over. Earlier we mentioned the BKL conjecture, which describes a chaotic, oscillatory approach to the singularity. In this frenzied dance, different directions of space expand and contract in an unpredictable, infinitely complex sequence. The system becomes so exquisitely sensitive that an infinitesimally tiny difference in the starting state leads to a completely different future evolution. But here is the ultimate twist at the true singularity. You cannot even define an infinitesimal difference. The sensitivity is infinite. Predictability evaporates not into mere complexity, but into true indeterminacy. This classical chaos then merges with quantum indeterminacy. If the universe's very first state was subject to quantum uncertainty, then it was not merely unknown to us, it was fundamentally indefinite, existing in a superposition of many possible configurations. Which one crystallized into our reality? There was no prior cause to decide. It was a truly random quantum roll of the dice, where the dice themselves were still forming. Consider the onset of cosmic inflation, the period of hyper-fast expansion thought to have smoothed and shaped our cosmos. Inflation requires a very specific, tiny patch of space to get started, a patch with just the right properties to trigger exponential growth. Where did that perfect patch come from? In a deterministic universe, it would be the inevitable outcome of prior conditions, but at the singular beginning, there are no prior conditions to determine it. That inflationary seed becomes a quantum fluctuation, a random event with no deterministic cause. Its existence, and by extension the existence of our entire vast universe, rests on a foundation of fundamental chance. To make this concrete, imagine a supremely powerful computer simulation tasked with recreating the universe. You program in all the laws of physics, every equation we have ever discovered. But when you go to input the starting values for density, temperature, and expansion rate, the software demands a number. The true initial condition, however, is not a number. It is mathematically a division by zero. If you try to force it, inputting the largest number the system can handle, the simulation immediately crashes, producing not a cosmos but an error code. This is not a failure of computing power, it is a revelation. The simulation crashes because the question it is being asked to deterministically evolve from a singular state has no answer. This loss of determinism forces a humbling revision of our place in the cosmos. We are not living out a story whose every detail was written at the beginning of time. Our universe is not a predetermined clockwork mechanism. Instead, we are the products of a chain of events that, at its very root, contains an element of irreducible randomness. The cosmic dice were thrown, and here we are, in one of the many possible worlds that could have emerged. This realization does not make the universe lawless, but it does mean the laws govern a reality born from a moment of fundamental indeterminacy. Our search for a complete causal story of existence may forever founder on this shore, where predictability itself was born from unpredictability. This ultimate loss of predictability forces us to confront a deeper, more unsettling boundary. We have reached a place where the language of science, the very framework of cause and effect, begins to dissolve into silence. The singularity may represent more than a physical limit. It could be the ultimate horizon of scientific inquiry, a point beyond which our empirical methods cannot reach. Here, the physicist must step back and the philosopher steps forward. For centuries, science has operated on the powerful assumption that every event has a cause, a principle known as sufficient reason. But what happens when we apply this logic to the totality of existence itself? The question, what caused the Big Bang, assumes the rules of causality that operate within our universe also apply to the origin of that universe. This may be a profound category error. The German philosopher Immanuel Kant argued that human reason inevitably runs into contradictions, antinomies, when it tries to grasp the unconditioned totality of the cosmos. We are trying to use the tools forged inside the container to examine the container itself. The singularity, then, is not merely a mathematical artifact. It is a signpost marking the limits of our cognitive framework. We must distinguish between the map and the territory. A mathematical singularity is a useful tool within a theory, a signal that the model has broken down. But does that breakdown correspond to a real, physical state of infinite density, or does it simply tell us our map is incomplete? This forces a pivotal choice in how we view our scientific theories. One response is instrumentalism, the view that theories are merely tools for prediction and organization, not literal descriptions of reality. From this perspective, general relativity is not broken at the singularity. It has simply reached the edge of its domain of usefulness, like a wrench that cannot turn a screw. Its job is to describe the universe from a certain point onward, not to describe its absolute origin. The infinities are not physical, they are flags telling us to switch tools. The opposite view is scientific realism, the belief that our best theories are approximating an objective reality. For a realist, the singularity's prediction is a catastrophic failure, a clear sign that the theory, however successful elsewhere, is fundamentally incomplete or wrong when pushed to the extreme. It demands a truer theory, one that eliminates the singularity entirely. Both views, however, lead to the same humbling conclusion. our current understanding is provisional. We are like the prisoners in Plato's famous allegory of the cave, who see only shadows cast on a wall and mistake them for the full reality. Our physics, for all its power and precision, may be the study of those shadows. The true nature of the cosmos, especially at its origin, may involve principles and dimensions forever outside the light of our cave. This invites a profound and reflective question. Is accepting a limit to our knowledge a form of intellectual surrender, or is it the ultimate mark of scientific maturity? To recognize a boundary is not to stop searching, but to understand the shape of the search itself. It shifts the goal from finding a single causal story within spacetime to understanding why spacetime and causality exist at all. This philosophical boundary even touches upon the most intimate mystery of all, the role of the observer. In quantum mechanics, the act of observation is inextricably linked to the reality that emerges. If the universe at its origin was a quantum state, does that imply a kind of proto-consciousness was inherent in its crystallization? Or are we, as conscious beings, simply the universe's way of looking back at itself, completing a loop that began in that first indefinite fluctuation? The edge of the Big Bang may be telling us that the story of the cosmos cannot be fully told without considering the strange loop of observation that brings it into being. This dizzying loop of observation brings us to one of the most profound and debated ideas in cosmology. If the universe seems improbably fine-tuned for our existence, is that because our existence is, in some way, a prerequisite for its reality? This is the Anthropic Principle, a concept that places the conscious observer at the center of the cosmic mystery. The physicist Brandon Carter, who coined the term, framed it with two distinct flavors. The weak Anthropic Principle simply states that what we can expect to observe must be compatible with the conditions necessary for our presence as observers. We should not be surprised to find ourselves in a universe capable of producing stars, planets, and carbon-based life, because that is the only kind of universe we could ever find ourselves in. It is a statement of selection bias. The strong Anthropic Principle takes a more provocative stance, suggesting the universe must have properties that allow life to develop at some stage in its history. This edges toward the idea that the existence of observers is not just a fortunate accident, but a necessary feature of reality itself. When applied to the enigma of the Big Bang singularity, this principle offers a radical lens. The inexplicably low entropy beginning, the precise expansion rate, the very fact that the laws of physics broke down in a way that allowed for a structured cosmos to emerge, could these conditions be explained by the requirement that they lead to us? In the context of a vast multiverse, the Anthropic Principle becomes a powerful tool of explanation. If an infinite array of bubble universes exist, each with different physical laws and initial conditions, then most will be sterile voids or short-lived collapses. Only a tiny fraction, like ours, will have the exact right settings for complexity and life. We find ourselves in one of those rare, hospitable universes not because it was designed, but because we are here to observe it. The singularity's fine-tuning, then, is not a puzzle to be solved by a deeper law within our universe, but a statistical inevitability across an infinite ensemble. It is the ultimate cosmic selection effect. Critics, however, argue this approach borders on a philosophical retreat. They contend that invoking the Anthropic Principle to explain the universe's properties is akin to a puddle of water marveling at how perfectly the hole it occupies is shaped. The puddle might think the hole was meticulously crafted to hold its exact form, when in reality, the puddle simply conformed to the shape of a random cavity in the ground. The principle, they say, does not explain why the multiverse landscape exists or why it contains any life-permitting universes at all. It risks being teleological, implying the universe had a goal or purpose. the development of conscious life which lies outside the realm of testable science. It can feel like explaining a mystery by appealing to an even bigger mystery. This leads to a reflective question that straddles science and philosophy. Is consciousness merely a late-stage byproduct of cosmic evolution, a flicker of awareness in a vast, indifferent machine? Or could it be something more fundamental, woven into the fabric of reality from the very first moment? Some interpretations of quantum mechanics suggest that observation plays an irreducible role in determining definite states from quantum possibilities. If we extend this logic to the universe's origin, it invites a staggering speculation. Did the universe require an observer to bring it into a definite state from its initial quantum haze? This is not to suggest humans caused the Big Bang, but that the property of observation, of information processing, might be a basic feature of a self-consistent cosmos. Perhaps the universe evolves in such a way as to guarantee the emergence of systems complex enough to observe it, completing a loop of self-awareness. While these ideas remain highly speculative and controversial, they underscore a crucial point. Our investigation into the edge of creation inevitably circles back to ourselves, to the nature of our own perception and inquiry. The Anthropic Principle, whether one finds it enlightening or evasive, forces us to confront the limits of a purely external, objective description of the cosmos. It suggests that any complete account of reality may need to include the curious fact that there are beings within it asking questions. This speculative realm, however fascinating, ultimately returns us to a more concrete challenge. If we cannot rewind the clock to witness the singularity directly, can we find any tangible evidence of those first moments imprinted on the universe we see today? The faint, uniform glow that fills the entire sky is the oldest picture we will ever have. This cosmic microwave background radiation is the cooled remnant of the universe's fiery youth, a snapshot from when it was just 380,000 years old. But within this seemingly smooth afterglow, scientists have discovered subtle imperfections, tiny temperature differences of just millionths of a degree. These are not flaws in the image, they are its most important feature, the fossilized imprint of the universe's most violent infancy. This ancient light is our only direct messenger from the edge of time, carrying whispers of physics at energy scales we can never recreate. The most successful framework for explaining the patterns in this light is cosmic inflation, the idea that the universe underwent a period of hyper-fast expansion in its first fraction of a second. Inflation does a remarkable job. It stretches a microscopic quantum fluctuation into cosmic scale, explaining the overall uniformity and the specific spectrum of hotter and colder spots we observe. Yet, by its very nature, inflation also acts like a cosmic iron, smoothing over the details of what came before. If a singularity or a bounce occurred, inflation's explosive growth would have stretched any direct evidence far beyond our observable horizon, effectively erasing the fingerprint of the initial state. This presents a profound challenge. The very process that explains the cosmos we see also hides the truth of its absolute origin. So we must look for subtler clues, for anomalies in the data that the standard story of inflation cannot easily explain. The European Space Agency's Planck satellite, which mapped this radiation with unprecedented precision, provided a stunning confirmation of the inflationary paradigm, but it also left us with intriguing puzzles. On the very largest scales, the cosmic microwave background shows a curious lack of correlation, as if part of the expected pattern is missing. There is also a famous cold spot, a region significantly cooler than the surrounding sky, that appears larger and more pronounced than our models predict. While these could be statistical flukes, they have fueled speculation that they might be scars from a pre-inflationary era, perhaps evidence of a collision with another bubble universe in a vast multiverse, or an echo of a chaotic pre-Big Bang phase. To test these ideas, scientists examine three key signatures in the ancient light with exquisite care. The first is the spectral index, which describes how the size of temperature variations changes with scale. Inflation predicts a nearly, but not perfectly, scale-invariant pattern, a specific slight tilt that Planck measured with great accuracy. Deviations from this prediction could point to different models of inflation or to alternatives like a bouncing universe. The second is a specific pattern of polarization in the light called primordial B modes. These are a potential smoking gun for inflation, as they would be generated by gravitational waves rippling through the fabric of spacetime during that explosive stretch. Detecting them would be like hearing the faint echo of the universe's birth cry. Their strength would tell us the energy scale of inflation, potentially linking it to grand unified forces. The third signature is non-Gaussianity. The standard inflationary picture predicts that the hot and cold spots in the cosmic microwave background should follow a particular bell curve statistical distribution. Finding significant deviations from this, shapes that are more complex or clustered, would be a major breakthrough. It could indicate interactions in the early universe that are too complex for simple inflation, perhaps hinting at the stringy or granular nature of spacetime at those incredible energies. Think of the cosmic microwave background not as a smooth photograph, but as a cracked and weathered clay tablet from the dawn of civilization. The overall text, the inflationary story, is clear and compelling. But the peculiar cracks, the faint impressions along the edges, might tell a different, older story, one about the tablet's formation before the writing began. What future experiments, like the Simons Observatory or the proposed Light Bird satellite, might detect in this ancient light could fundamentally reshape our understanding? They are not looking for a picture of the singularity itself that is forever beyond our view. Instead, they are forensic scientists searching for consistency. Does the story told by this 380,000-year-old fossil align with the stories told by our boldest theories of quantum gravity and cyclic models? Or does it point to a narrative we have not yet dared to write? The silence of the data, the absence of a predicted signal, can be as telling as a discovery. The cosmic microwave background offers data, but what guides us where data cannot reach? When direct experimentation is impossible, physicists turn to a different kind of compass, the relentless pursuit of mathematical consistency. At the edge of the Big Bang, we cannot run a lab experiment or build a telescope to peer beyond. Instead, we ask a profound question: what mathematical story holds together without tearing apart at the seams? This search for internal harmony, for equations that do not spit out infinities or contradictions, becomes the primary method for navigating the unknown. The mathematician Eugene Wigner once marveled at the unreasonable effectiveness of mathematics in the natural sciences. It is as if the universe speaks a hidden language, and mathematics is our key to deciphering its grammar. When facing the singularity, this reliance on mathematical beauty and logic is not a luxury, it is a necessity. Theories like string theory and loop quantum gravity are pursued not because we have seen their predictions confirmed, but because they offer a mathematically consistent framework where general relativity's equations simply fail. They remove the pathological infinities and provide a well-defined description of extreme regimes. This drive for consistency uses specific, stringent criteria as filters. One is unitarity, the principle that information is never destroyed. A theory of quantum gravity must respect this, ensuring that what goes into a black hole or emerges from the Big Bang is in principle recoverable, preserving the logical flow of cause and effect. Another is locality, the idea that objects are only directly influenced by their immediate surroundings. Yet quantum entanglement and holography challenge this, suggesting that at the deepest level, reality may be profoundly non-local. Then there is renormalizability, the requirement that a theory's equations yield finite, sensible answers rather than infinite nonsense. General relativity is not renormalizable, which is why its predictions blow up at the singularity. A viable theory of quantum gravity must solve this. We have seen this kind of mathematical crisis drive progress before. At the turn of the 20th century, classical physics predicted that a hot object should emit infinite ultraviolet radiation, a nonsensical result called the ultraviolet catastrophe. To resolve it, Max Planck introduced a radical idea that energy is quantized. This mathematical fix to ensure consistency did not just solve a calculation, it birthed quantum mechanics and reshaped our understanding of reality. Today, the singularity presents a similar but far greater catastrophe. The search for a mathematically consistent theory of quantum gravity is, in essence, the search for the next Planck, for the conceptual leap that turns infinite errors into a new law. This pursuit often unfolds through thought experiments, rigorous logical explorations of what a theory implies. Einstein famously used thought experiments about trains and elevators to develop relativity. Similarly, physicists today use thought experiments about falling into black holes or the universe's first moment to test their mathematical frameworks. They ask, if this equation is true, what must logically follow? The goal is a unique, self-consistent mathematical structure that leaves no loose ends. Does this mean mathematical beauty is a reliable guide to physical truth? It is a deep and reflective question. History shows that elegant, consistent mathematics often precedes major discoveries, from Paul Dirac's equation predicting antimatter to the Standard Model's symmetrical structure. Yet there is no guarantee. A theory can be mathematically gorgeous and completely wrong about our universe. The final judge must always be observation, but when observation is forever out of reach, consistency becomes our best and only torch in the dark. This abstract quest often leads to astonishing and unexpected connections, tying the physics of the cosmos to deep problems in pure mathematics, computer science, and even the philosophy of information. The most profound clues about the cosmos may not come from telescopes, but from tabletop experiments. A revolutionary bridge is being built between the science of the unimaginably large and the physics of the everyday, between cosmology and condensed matter physics. Here, in laboratories around the world, researchers are creating tiny, controlled universes to simulate the breakdown of physics at the edge of a black hole. This field is called analog gravity, and it starts with a stunning mathematical coincidence. The equations that describe how sound waves move through a flowing, compressible fluid are almost identical in form to the equations that describe how light moves through the curved spacetime of general relativity. In the fluid, the flow plays the role of spacetime curvature. If you can make a fluid flow faster than the local speed of sound, you create a sonic point of no return, an acoustic event horizon. Sound waves downstream cannot fight their way back upstream, just as light cannot escape a gravitational black hole. The physicist William Unruh, who pioneered this idea, called these laboratory creations dumb holes. Within them, the smooth description of sound waves in the fluid breaks down at a central point, forming an acoustic singularity. This is not a true gravitational singularity of infinite density, but it is a precise mathematical analog where the equations governing the phonons, the quantum particles of sound, become singular and fail. By studying how physics breaks down at this engineered point in a superfluid helium bath or a carefully tuned Bose-Einstein condensate, we gain a physical intuition for what might happen at the real cosmic edge. We can literally watch an analog of spacetime curvature emerge from the collective behavior of countless atoms, a phenomenon that is not built in, but that arises from their interactions. This is the concept of emergent spacetime. Consider a specific experiment. Researchers take a container of superfluid helium, a fluid with zero viscosity that can flow without friction. They set it into a carefully controlled rotation or push it with lasers to create a whirlpool with a draining flow at its center. At a certain radius, the flow velocity exceeds the speed of sound in the helium. They have made a dumbhole. Now, according to UNRA's calculations, this acoustic horizon should produce an analog of Hawking radiation. Just as a real black hole is predicted to emit a faint thermal glow due to quantum effects at its horizon, the dumbhole should emit a faint spectrum of phonons. Detecting this in the lab is extraordinarily difficult, but the attempt itself is transformative. It allows us to test the quantum physics of horizons in a controlled, repeatable setting. The analogies extend beyond fluids. In certain optical fibers, pulses of light can create effective event horizons for other light waves. In sheets of graphene, the collective excitations of electrons behave as if they are moving through a curved cosmic geometry. Each of these systems is a universe in a box governed by its own rules, yet sharing a deep mathematical kinship with Einstein's cosmos. These experiments force a profound reflective question upon us. If we can so readily create analog spacetimes and singularities in a dish of superfluid, could our own spacetime be a similar kind of emergent phenomenon? Perhaps the four-dimensional continuum we inhabit is not fundamental. It might be a macroscopic approximation, a kind of cosmic fluid that emerges from the quantum entanglement of countless more basic elements, just as the flow of a liquid emerges from the chaotic dance of its molecules. The smooth geometry of general relativity would then be a kind of thermodynamics for spacetime, a large-scale description that hides a bustling, discrete quantum reality underneath. This interdisciplinary insight enriches our conceptual toolkit immeasurably. It tells us that the singularities where physics breaks down may not be unique to gravity. They appear wherever a smooth, classical description is pushed beyond its limits by underlying quantum granularity. By studying the breakdown in our laboratories, we are learning the grammar of emergence, which may be the very language needed to write the next chapter in the story of our universe's origin. The faint echoes of creation may still be ringing through the cosmos, waiting for us to learn how to listen. While we can never witness the singularity directly, the universe may have left a hidden recording of its most violent first moments, not in light but in the trembling of spacetime itself. These are primordial gravitational waves, ripples in the fabric of reality generated when the universe was a seething quantum foam. Detecting them would be like finding the fossilized vibrations of the Big Bang, a direct signal from an era forever beyond the reach of telescopes. The challenge is almost incomprehensible. These waves would have stretched to wavelengths larger than our entire galaxy over billions of years, their signal now buried in a sea of cosmic noise. To find them, we must build the most sensitive listening devices ever conceived, not on Earth but in the quiet of space. One such ambitious project is the Laser Interferometer Space Antenna, or LISA. Imagine 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. They would form a gravitational wave observatory so vast it could detect the subtle stretching of space caused by the merging of supermassive black holes and perhaps the faint hum from the universe's birth. The key lies in the spectrum of these waves, the pattern of their strength across different frequencies. Different theories of the beginning paint different pictures on this cosmic canvas. The standard story of inflation predicts a characteristic, nearly flat spectrum. But if the universe underwent a quantum bounce, as in loop quantum cosmology, the equations show a dramatic amplification of gravitational waves at very specific low frequencies. It would be like hearing a distinct, deep bass note in the cosmic symphony that inflation alone cannot produce. String theory scenarios might leave a different signature altogether, perhaps a series of resonant peaks imprinted during a pre-Big Bang contraction phase, like the harmonic overtones of a plucked string. These are not minor variations. They are the unique fingerprints of physics operating at energies 1,000,000,000,000 times beyond what any particle collider could ever reach. Beyond gravitational waves, other messengers could carry clues. Ultra-high energy cosmic rays, particles with energies millions of times greater than those produced in our largest accelerators, might hint at processes from the early universe's unification of forces. A diffuse background of relic neutrinos, the ghostly particles that flooded from the hot Big Bang, holds a perfect snapshot of the universe just 1 second old, though catching them is a monumental task. Even the cosmic microwave background itself might hold further secrets in the form of spectral distortions, tiny deviations in the color of the ancient heat that could be caused by the release of energy in the very first moments. The search is akin to listening in a vast, echoing canyon long after a single shout. You cannot hear the original sound, but by carefully analyzing the pattern of echoes bouncing off the distant walls, you can deduce the shape of the canyon and the nature of the event that caused them. Our universe is that canyon, and the primordial gravitational wave background is the faintest, most ancient echo. What would it mean if we finally heard it? A clear detection would do more than confirm inflation or a bounce. It would provide our first experimental data on quantum gravity itself. It would tell us if spacetime is smooth or granular, if extra dimensions exist, or if the universe truly cycled through a previous phase. It would transform the singularity from a purely mathematical boundary into a physical process we can begin to characterize. The technological challenge is a perfect mirror of the conceptual one. Building an instrument sensitive enough to measure distortions smaller than the width of an atom across a distance larger than the orbit of Earth requires pushing engineering to its absolute limits. It is a testament to our desire to know, a physical manifestation of the question that has driven this entire journey. We are building a machine to listen to the birth of time, hoping to hear the universe tell us how it truly began. The equations of quantum gravity may be so complex that they can only be solved by the very phenomena they describe. To truly grasp what happened at the edge of the Big Bang, we might need to build a new kind of universe in a machine, not with gears and wires, but with entangled quantum bits. This is the frontier of quantum simulation, where the goal is not merely to calculate, but to recreate the dynamics of creation itself within a controlled, artificial system. The challenge is one of overwhelming complexity. In a classical computer, information is stored as bits, zeros and ones. Simulating a quantum system, like the early universe, requires tracking the probabilistic state of every possible configuration. For just a few particles, this is manageable. But for the quantum fields that constituted the infant cosmos, the number of possible states grows exponentially. A system with 300 quantum bits could represent more states than there are atoms in the visible universe. No classical supercomputer, no matter how powerful, could ever hold that information. This is where quantum computers offer a tantalizing path. Instead of simulating quantum behavior, they can embody it. A quantum computer uses qubits, which can be in a superposition of 0 and 1, and can be entangled with each other, creating a network that directly mirrors the quantum connections that may have woven the fabric of spacetime. Researchers in quantum simulation are pioneering this approach for field theories, the mathematical frameworks that describe forces and particles. Their aim is to map the equations of a candidate theory of quantum gravity onto the interactions of qubits in a processor. By carefully tuning these interactions and observing the outcome, they could watch a miniature model of spacetime geometry emerge from quantum entanglement, much like watching a crystalline structure form from a cooling liquid. One prominent strategy is lattice quantum gravity. Here, physicists replace the smooth, continuous spacetime of general relativity with a discrete grid or lattice, like a cosmic mesh of interconnected points. They then use techniques like Monte Carlo simulations, which employ random sampling to approximate incredibly complex sums. to study how this lattice behaves under the rules of quantum mechanics. The immense challenge is ensuring that as you take the lattice spacing to zero, recovering a smooth continuum, the physics you care about remains intact and doesn't vanish into numerical noise. Specific projects are turning these ideas into experiments. Some teams use tensor networks, intricate mathematical structures that represent the quantum wave function of a system, to study the possible initial states of the universe. These networks visually capture how entanglement binds different regions of space, offering clues about how a smooth cosmos could condense from a quantum haze. Others are designing quantum algorithms to tackle equations like the Wheeler-DeWitt equation, which famously describes the quantum state of the entire universe and notoriously lacks a time variable, presenting a monumental puzzle for any simulation. To grasp the scale of this computational problem, consider our struggle to simulate turbulent fluid dynamics, like the chaotic swirls in a hurricane or a star's interior. Even with our most powerful supercomputers, these simulations require approximations and can only capture a limited range of scales. Now, imagine that challenge, but for the turbulence of spacetime itself at the Planck scale, where the very grid of your simulation is what you are trying to understand. The fluid is the stage, and you are trying to simulate the stage while standing on it. This leads to a profound, almost philosophical question. If we one day run a perfect quantum simulation of the universe's first moments, and it shows a clear, consistent picture of a bounce or a tunneling event, would that be considered real understanding? Or would it just be a self-consistent model inside another universe, our own? A simulation is, after all, a map, and as we have learned, every map has its limits. The cultural resonance of this pursuit is deep. We are attempting to build a mirror for Genesis, to hold a reflection of our own origin in a machine of our own making. It is a quest that blends the most abstract theoretical physics with the most advanced engineering, driven by a timeless human desire to witness our own beginnings, even if only in the glow of a quantum processor's cold, ordered light. The drive to understand our beginning is not new. It is a story humanity has been telling itself for as long as we have had stories to tell. Before telescopes and equations, we looked at the stars and wondered, how did all of this come to be? The answer across countless cultures often took a strikingly similar shape: a formless void, a cosmic egg, a singular point from which everything emerged. The Norse spoke of Ginnungagap, a yawning gap between fire and ice, a chaotic nothingness that gave birth to the first giant. Ancient Hindu texts describe Brahman, the ultimate, singular reality from which the entire universe of forms and names manifests. In many West African traditions, the world began from a tiny seed or a single thought in the mind of a creator. These are not failed science, they are profound mythology, humanity's first attempts to grapple with the ultimate question using the language of symbol and narrative. They reveal a pattern. When faced with the mystery of existence, the human mind instinctively reaches for the concept of a singular origin, a moment or state so fundamental it defies ordinary description. This is the deep cultural echo of the Big Bang singularity. We are not comparing myth to physics to say they are the same. A creation story is a framework for meaning, a way to place human life within a cosmic order. A scientific theory is a framework for prediction and understanding, built on evidence and mathematics. Their purposes are different, but their shared focus on that initial, transformative moment is telling. It points to a universal curiosity, a deep-seated need to look back to a beginning, even when that beginning retreats into the realms of chaos or the unknowable. Consider the pervasive motif of the cosmic egg. From the Orphic myths of ancient Greece to the Pan-Gu story of China, a common narrative tells of a primordial egg floating in a formless void. Inside, the opposites of the universe, heaven and earth, light and dark, are held in perfect, compressed unity. Then it cracks, The act of breaking releases and differentiates all that exists, creating the ordered cosmos from that single, unified source. The imagery is hauntingly familiar. It is a mythological analog for the singular point of infinite density, containing all potential, that then expands and differentiates into the universe we know. The egg is a finite, graspable symbol for what is ultimately an ungraspable concept. Modern storytelling continues this tradition. In literature and film, when creators grapple with cosmic origins, they often return to these ancient themes. Whether it's the monolith in 2001, A Space Odyssey, an enigmatic object that triggers a leap in consciousness and seems to point to an external architect, or the existential questions about simulation and creation in the Matrix, these narratives explore the anxiety and wonder of a universe with a beginning we cannot fully comprehend. They are our modern myths, using the language of technology and science fiction to ask the same old questions. Why does this pattern persist across millennia and disciplines? Perhaps because the origin is the ultimate horizon. Just as we each have a personal story that begins with our birth, we seek a birth story for everything. To not have one feels like a narrative without a first chapter, an equation without a starting value. The singularity, whether in myth or in physics, represents that threshold. It is the boundary beyond which our familiar tools of understanding, whether they are words, stories, or classical equations, simply stop working. In mythology, that boundary is often guarded by gods, monsters, or sacred mystery. In science, it is guarded by infinities and the limits of our theories. Both acknowledge a frontier of the knowable. This human context softens the sometimes cold abstraction of the physics. It reminds us that the search for the beginning is not just a technical puzzle to be solved. It is part of a much older, more profound search for meaning and place. We look to the singularity not only to complete our equations, but to complete a story. What does it mean that we live in a universe that had a starting point? Does that imply something before, or does it force us to redefine what before even means? These are questions that physics can frame but cannot answer alone. They live in the space where science meets philosophy, where calculation meets contemplation. By seeing our scientific quest alongside humanity's long mythological conversation, we see it for what it truly is: the latest, most powerful chapter in an eternal human endeavor to turn our face toward the dawn of everything and ask, how? The ultimate lesson from the edge of the Big Bang may be that some questions have no final answers, only better ways of asking them. This presents a profound challenge for anyone who teaches science. How do you explain a place where the rules themselves stop working? The task is not to provide a tidy conclusion, but to guide students to the frontier of human understanding and show them the map ends there. It requires a delicate balance, presenting the solid ground of established theories like relativity and quantum mechanics, while honestly revealing the chasms that open between them. Science educators often speak of threshold concepts, ideas that are transformative and irreversible once understood, but also troublesome and counterintuitive. The cosmological singularity is a supreme threshold concept. It forces a learner to let go of the expectation that every physical question has a neat, calculable answer within our current framework. The goal shifts from delivering facts to cultivating a specific kind of wisdom, one that embraces wonder alongside intellectual humility. A skilled teacher might begin with a graph of a simple function, like 1 divided by x. On the whiteboard, they draw the curve swooping upward toward positive infinity as it approaches 0 from the right, and plunging downward toward negative infinity from the left. Then they point directly to the gap at x equals 0. This is not a point on the graph, it is where the graph stops making sense. The equation produces an error, not an answer. This mathematical breakdown is a precise analogy for what happens in our cosmological equations at time 0. The infinities are not descriptions of a physical state. They are error codes in the calculation, bright red flags telling us our model has exceeded its domain of validity. This distinction between mathematical infinity and physical reality is crucial to grasp. Students often misinterpret the singularity as a place of unimaginably large numbers, but it is more accurate to think of it as a place where the very question of size becomes undefined. Effective visualizations can help. Imagine a computer simulation of the expanding universe running in reverse. Galaxies rush together, space contracts. The temperature and density readings on the screen climb higher and higher. Then, just as the numbers are about to flip into an overflow error, the screen freezes. The simulation does not show a final, infinite number. It crashes. This crash is not a failure of the software, it is the point. It demonstrates that the model underlying the simulation, general relativity, cannot process the input. The breakdown is the lesson. Thought experiments are another powerful tool. Ask a classroom to consider measuring the size of the universe at the moment of the Big Bang. They would need a ruler, but to place that ruler, there must be a space to put it in. At the singularity, there is no container space outside the universe to hold the ruler. The question itself assumes a framework that does not exist. This exposes common misconceptions head-on. One is the idea of the universe exploding into a pre-existing void. Teachers must clarify that space itself is expanding, not filling an emptiness. Another is the search for a cause that came before. This requires patiently explaining that if time itself began with the universe, then causality, as we know it, may not apply to the origin. The most important pedagogical shift is to highlight the process of scientific inquiry over the possession of certain knowledge. The singularity is not a dead end for science, it is a vibrant frontier. It is the anomaly that drives the entire field of quantum gravity research. By showing students the open questions, what replaces the singularity? Does time have a beginning? An educator transforms a topic from a static fact in a textbook into a living, breathing mystery. This approach fosters a deeper scientific literacy. It teaches that science is not a collection of answers, but a disciplined method for asking questions, even when those questions lead to the edge of the knowable. The educational journey circles back to a personal impact. Confronting the limits of our knowledge can be unsettling, but it can also be liberating. It invites each of us to participate in the great story of discovery, to feel the awe that comes from standing before a genuine mystery. In the end, teaching about the breakdown at the beginning is not about imparting despair, but about passing on the torch of curiosity, illuminating not just what we know, but the vast and beautiful darkness of what we have yet to understand. That profound humility we feel before the mystery is not an end, but a beginning. When we accept that our most fundamental laws break down at the edge of everything, it forces a quiet revolution in how we see ourselves. The singularity whispers that permanence is an illusion, not just of our lives, but of the cosmos itself. The stage upon which our story unfolds was born from a state that defies every rule of the stage. This realization can be deeply disorienting, but within that disorientation lies a profound and liberating awe. We are not living in a clockwork universe where every tick was predetermined at the moment of creation. The breakdown of predictability means we are part of a story with genuine novelty, a cosmic narrative that chose one path from a haze of quantum possibility. Our existence, then, is not a pre-written script, but an ongoing, creative expression of the universe, emerging from a first moment that was, in essence, a creative act of lawlessness. Carl Sagan's reflection on our world as a pale blue dot gains a new dimension when viewed through this lens. He urged us to see our planet as a mote of dust suspended in a sunbeam, emphasizing the fragility and unity of our home. But extend that vision backward through time to that singular point. Every human triumph and tragedy, every mountain and ocean, every star in every galaxy, was compressed into a state where those words have no meaning. From that perspective, our divisions, our borders, and our conflicts are not just small. They are temporary patterns etched onto a reality that is far stranger and more fluid than we ever supposed. This cosmic humility is not about making us feel insignificant. It is about redefining what significance means. Our significance lies not in commanding the universe, but in being the part of it that can look back, wonder, and try to understand. Embracing a fundamental mystery is not a surrender of intellect. It is its highest exercise. To stare into the singularity and admit we do not know is to be rigorously honest with the evidence. This intellectual liberation frees us from the need for tidy, complete answers and opens us to a universe of breathtaking depth. It transforms our relationship with the unknown from one of frustration to one of reverence and curiosity. Consider the experience astronauts describe when viewing Earth from orbit, the overview effect. They speak of a sudden cognitive shift, a visceral understanding of the planet's unity and fragility, stripped of all imaginary line. Now try to imagine the cosmological overview effect. If we could somehow step outside all of spacetime and look back at the entire history of the cosmos, from the silent singularity to the spiraling galaxies and thinking beings, what would we feel? We would see not a static sculpture, but a dynamic, unfolding process, a single, coherent event of which we are an intimate part. Our transient lives are not separate from the cosmic story. They are its latest, most intricate chapters. So how does this change our worldview on a personal level? Does knowing the laws of physics break down make our daily struggles feel trivial, or does it infuse them with a new kind of meaning? It invites us to see our brief moment of consciousness as a rare and precious gift of a universe that became complex enough to know itself. We are not passive inhabitants of a fixed reality. We are active participants in a cosmos that is still becoming, whose very origin remains an open question. This understanding does not provide easy answers about purpose, but it frames our existence within the grandest possible context. We are the universe grown to a point where it can contemplate its own birth, and in that contemplation, with all its humility and wonder, we find a deep connection to the mysterious source from which everything, including our capacity to ask, ultimately flows. Each pillar of physics does not fall alone. When we isolate the collapse of spacetime, the indeterminacy of quantum laws, the mathematical errors, and the failure of thermodynamics, we see separate crises. But their true power lies in their connection. They are not isolated failures in a stable structure. They are interlocking parts of a single, coherent framework, and at the edge of the Big Bang, that entire framework unravels in a synchronized cascade. The universe runs on a web of dependencies. Time requires space to give it measure. Space requires geometry to give it shape. Geometry requires matter and energy to curve it. Matter and energy require quantum fields to define them, and those fields require a stable spacetime arena to exist within. Pull one thread, and the whole tapestry begins to fray. At the singularity, we do not pull one thread. We grasp the tapestry at its very first knot and pull everything at once. Without a functioning concept of spacetime, there is no stage for the quantum fields of the standard model to play upon. Without those fields, there are no particles. Without particles, there is no matter to curve geometry, no energy to drive thermodynamics, and no medium for information to be processed or preserved. Every concept we use to describe reality presupposes the existence of the others. This is why the breakdown is so comprehensive. Relativity's infinite curvature is not a separate problem from quantum mechanics' infinite probabilities. They are two expressions of the same underlying impossibility, the attempt to describe a state where the container and the contained, the stage and the actors, have not yet differentiated. Think of it like a house of cards. Each card is a major theory or concept: gravity, quantum fields, thermodynamics, leaning against the others for support. The bottom card, the foundation, is the assumption of a smooth, classical, pre-existing arena. At the edge of the Big Bang, that bottom card is violently removed. The entire structure does not just wobble, it collapses into a formless heap because the cards were defined by their relationships to each other. Remove their shared context, and their individual identities become meaningless. This synthesis reveals the central, unifying paradox at the heart of the quest for a theory of everything. Such a theory must be capable of describing the universe's own boundary conditions. It must be a set of rules that can explain how those rules themselves came into being. It needs to be self-booting, like a computer that can turn itself on without anyone pressing the power button. Our current physics is not like that. General relativity needs you to input the initial shape of the universe. Quantum mechanics needs you to define an external clock and a vacuum state. They are programs that require a user to hit run. But at the beginning, there is no external user, no outside clock, and no pre-formatted vacuum. The theory must contain, within its own logic, the seed of its own initialization. This is the monumental challenge that now lies before theoretical physics. It is no longer enough to find equations that work within the universe. We must find a framework so complete, so self-contained, that it can account for its own existence, bridging the chasm between absolute nothingness and the rich, structured reality we inhabit. The journey ahead is not merely one of greater complexity, but of a fundamental reimagining of what a physical law even is. The ultimate theory cannot simply patch over the cracks in our current models. It must rebuild reality from new foundations, accomplishing a set of tasks so demanding they stretch the limits of human imagination. To truly describe the edge of the Big Bang, a future framework must be more than just consistent. It must be a theory of everything, a complete and unified description of nature that meets several non-negotiable criteria. First and foremost, it must be non-singular. This means its equations must describe the universe's earliest moments without producing infinities or errors. There can be no point where the mathematics breaks down. Instead of a catastrophic endpoint, the theory must provide a smooth, well-defined transition, whether from a quantum bounce, a tunneling event, or some other process we have not yet conceived. It must tell a story with a clear plot, not one that ends with a torn-out page. Second, it must be background independent. This is a subtle but profound requirement. Our current theories, even quantum mechanics, assume a fixed stage. They need a pre-existing spacetime arena, a static vacuum, or an external clock to make sense. But at the beginning, there is no pre-existing stage. The theory itself must generate the stage as part of the play. It must describe how spacetime, and even the concept of time itself, emerges from something more fundamental, like a network of quantum relationships. As physicist Lee Smolin has emphasized, a background-independent theory treats the geometry of the universe not as a fixed container, but as a dynamic, evolving actor in the cosmic drama. Third, the theory must be unitary. In quantum mechanics, unitarity is the principle that information is never destroyed. It can be scrambled like an egg, but never erased from existence. A theory of everything must preserve this quantum logic, even at the Big Bang. This ensures that causality, in its deepest quantum sense, remains intact. The universe's origin cannot be a true erasure of the rulebook, just a transformation of it. Finally, and crucially, any candidate theory must reduce to known physics in the appropriate limits. Once the universe expands and cools beyond the Planck epoch, its predictions must seamlessly morph into the equations of general relativity and the standard model of particle physics. It cannot invent a completely alien reality that contradicts the stunningly accurate science we have already verified. It must contain our current understanding as a special case, much like Einstein's relativity contains Newton's laws as an approximation for slow speeds and weak gravity. Beyond these formal requirements, the theory faces an even deeper philosophical challenge. It must explain the initial conditions. Why did the universe start with such astonishingly low entropy and such precise fine-tuning for complexity? This pushes the theory into a difficult tension. Does it predict a unique universe, ours, with all its specific properties, or does it naturally lead to a plurality, a vast landscape of possible universes in a multiverse, with ours being just one statistically likely outcome among many? This is not just a technical detail. It strikes at the heart of why we are here. To grasp the scale of this ambition, think of the historical quest for the periodic table of the elements. Before Mendeleev, chemistry was a chaos of disparate substances with no organizing principle. The periodic table brought order, revealing that every element was a variation on a theme, its properties dictated by its place in a logical structure. It didn't just catalog what was known, it predicted the existence and properties of elements not yet discovered. A theory of everything aims to be the periodic table for fundamental physics, but on a cosmic scale. It would reveal the underlying theme from which all forces, all particles, and the very fabric of spacetime are variations. It would not just describe our universe, but explain why this particular set of variations came to be. Yet this monumental goal leads to a reflective and humbling question. Is a final, complete theory of everything even possible? Or is human understanding an endless frontier where each answer reveals a deeper layer of questions? Some argue that the universe, being a single, unique entity, may not be derivable from pure logic alone. There may be brute facts, initial conditions that simply are, with no deeper explanation. Others hold out hope for a beautifully simple equation, an elegant seed from which all complexity flowers. This forward-looking perspective does not promise a quick answer. It defines the shape of the quest itself. We are searching for a narrative that can hold the singularity without breaking, a story that begins before time and explains its own telling. Whether we ever find it or not, the search reshapes our understanding of reality, teaching us that the universe is far more strange, connected, and creatively unstable than we ever dreamed. This journey to the edge of existence leaves us with a universe far stranger than we began with. We have seen our two greatest theories, the pillars of modern physics, shatter against the same impossible point. General relativity's elegant geometry dissolves into infinite curvature, while quantum mechanics offers only infinite probabilities. Their combined failure is not a minor gap, but a chasm in our understanding, revealing that the smooth, continuous reality we perceive is an illusion that breaks down at the beginning. At that threshold, time loses its meaning, space collapses into a geometric error, and every concept from temperature to causality ceases to function. The terrifying infinities that appear in our equations are not descriptions of a physical state. They are the ultimate error messages, mathematical screams that our current framework has reached its absolute limit. This profound breakdown is not the end of the story, but the starting signal for a new one. It has driven physicists to propose breathtaking alternatives, from cosmic bounces and holographic projections to multiverses and quantum tunnels from nothing. Each is an attempt to write a narrative where the universe does not begin with a nonsensical break, but with a coherent transition. The search for a theory of quantum gravity, therefore, is far more than an academic puzzle. It is a quest to understand the very nature of existence, to find the foundational language from which time, space, and matter themselves are spoken. Our current scientific framework is incredibly powerful, but it carries inherent limits, boundaries that become starkly visible only when we dare to look all the way back. The physicist John Archibald Wheeler offered a beautiful metaphor for this endless pursuit. He said, "We live on an island surrounded by a sea of ignorance." As our island of knowledge grows, so does the shore of our ignorance. Every answer we find at the edge of the Big Bang expands our island, but it also lengthens the coastline, revealing new and deeper questions we had not even thought to ask. This exploration reminds us that the unknown is not a barrier to be feared, but an invitation to wonder. It is the source of all discovery. So I am curious, what aspect of this ultimate mystery stays with you? Is it the dissolution of time, the quantum foam, or the haunting idea of a universe tunneling into being? Share your thoughts and questions in the comments below. I would love to hear what resonates. If you enjoyed this journey to the frontier of cosmology, please subscribe for more explorations into the deepest mysteries of space and science. Thank you for watching, and remember, the greatest adventure lies just beyond the edge of our understanding. Keep looking up.